Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video we will discuss another popular probability distribution, the hypergeometric distribution. We're going to begin our discussion with an example. By the way, you can find this example in our lecture notes. Here goes our example. So, the idea is that we want to select 2 additional jurors to complete a jury, right? And we have 6 candidates. 2 of them are women and 4 remaining are men. These 2 jurors, right, are going to be randomly selected from the group of our 6 candidates. So the random variable that we're interested in is y, and y represents the number of women in this group of 2 additional jurors. Make sense? Okay, and furthermore, we would like to find the probability distribution of y and the expected value of y. Make sense? Okay. So let's try and solve this problem. We are going to proceed in a similar manner to what we have been doing in the past with other probability distributions. First, we're going to describe the random experiment. Then we are going to obtain the sample space. Once we have the sample space, in this case the random variable is already defined, but we're going to just recall what's a random variable of interest, and finally we are going to be in a good position, in a good place to derive the probability distribution of y. Okay, so as I said, first step, let's describe the random experiment. So random experiment. So what we're going to be doing is drawing a sample of size 2 from a population that consists of 6, right? 6 items. 6 items. In general, when we refer to the population size, right, that we are drawing our candidates from, we're going to be using the letter capital N, okay, for the population size. Okay, next, it turns out that not all items in this population are considered as successes. So let me say that in this case, since the random variable of interest is the number of women, right, selected, right, to serve as part of the jury, right, it turns out that only 2 of them are women, so we only have 2 successes in this small population. Okay, so 2 of these items are successes. By the way, in general, we're going to be using the letter R, lowercase r to refer to the number of successes in our population of interest. Okay, and naturally, if we have a population of size 6 and only two of them, only two of the items in that population are considered successes, then the remaining items are going to be considered as failures, right? And it makes sense that n minus r represent the items considered as failures, right? So, and for n minus r, which in this case is 4, and 4 of these items are failures. And just like in for instance, when we talked about binomial distribution, these labels of success and failure are relative to what you are interested in. Okay? Okay. So, sample space. Let me use that capital Greek O, omega, to denote the sample space. Okay? Okay. So let's construct the sample space. Let's remember that we have a population of size 6, and we have 2 women. So let me use W sub 1 for a woman number 1. Let me use W sub 2, W2, for woman number 2, and we're going to have something similar for the 4 men that are candidates to serve in this jury. Okay. Okay. So there we are. Okay. So omega, we can think of omega as a sequence, right? A sequence of length 2, where the first one represents the first candidate selected to serve as part of the jury, right? And the second entry of this sequence would be the second candidate selected. Okay, so one possible outcome of that random experiment would be this, right? That sequence. The 2 women are selected to serve as part of the jury. Another possibility would be, instead of that, say this: woman number 1 and man number 1. Okay, makes sense? And we can continue like that, right? Woman number 1 and man number 2. Woman number 1, man number 3, and woman number 1 and man number 4. We could also have something similar, right, to what we have here, but instead of the first woman being selected, we could have the second woman instead. right? Now, another possibility would be, now we have man number 1 and man number 2. Man number 1, man number 3, man number 1, and man number 4. Okay, makes sense? We could have those as possible outcomes. So let me copy paste here to save a little bit of time. And we said we could have this guy here, right? Another one would be, you know, man number 2 and man number 3, man number 2 and man number 4. So let's do that. And finally, man number 3 and man number 4. Right? Makes sense? Okay. Now, note that the total number of these sequences equals 6 choose 2, right? Let's write that down. Note that the total number of possible sequences, or in this case, well, we have samples, is given by 6 choose 2, right? And we can check, right? So so we have 1, 2, 3, 4, 5, then we have 4, then we have 3, then we have 2, then we have 1, and the sum of 5 plus 4 plus 3 plus 2 plus 1 equals 15, right? And let's check using R that 6 choose 2 gives you 15. So choose 6 comma 2 15, okay, which makes sense because in this case order doesn't matter, right? W2 and M1 is the same as M1 and W2. Order doesn't matter in this case. So using combinations, we're going to be able to find you know, the different samples that result from this experiment. Make sense? Okay. Okay, so let's remind ourselves what y represents. Just going to copy and paste y, the random variable of interest, right? Random variable y is number of women in this group, right? Okay. So part A was about giving the probability distribution of y. And again, remember, when we say the probability distribution of a random variable, what we mean is just a list of all possible outcomes along with the corresponding probabilities. Okay, so first we need to construct the probability distribution of y. We need the list of possible outcomes. So we are sampling, we have samples of size 2. Okay, so and we are counting the number of women included in that sample, right? So the results for that experiment would be 0 women included in that sample of size 2, 1, or 2. Okay, so those are the possible values for that random variable, and we want, as we said, the corresponding probabilities for each of those outcomes. So given that we have taken the time to construct the sample space, if we want to, find the probability for y equals 0, we just have to count the number of outcomes that give you that value, that are equivalent to that value for the random variable y. So in how many of these possible samples we don't observe a woman included? So we just count, right? So if 0 women are included, this would be one case, right? M3 and M4. 1, 2, 3, 4, 5, and 6, right? The others include at least 1 woman. Okay, so we have 6, and out of a total of 15. And the thing is that we are, making this selection. We're drawing that sample so randomly, and any of these samples has the same probability of actually being the one observed, so they are equally likely. So what we have here is 6 divided by 15, right? Makes sense? So 6 divided by 15. We're just counting, right? Let's find the probability that y equals 2. So how many of these sequences include 2 women exactly? So only one of them, right? So 1 in 15. Finally, we could find the remaining value, right, in 2 ways. We could count, or we could use the properties of a probability function. So we know that the sum of these guys should be 1, right? So this guy should be 8 divided by 15, right? Or we could count, and if we counted, we would realize that yes, we have 8 cases where we have exactly 1 woman included, right? So if we count, it would be 1, 2, 3, 4, and these 4 cases, 8, right? So it makes sense. Okay, so now we have the probability distribution. That's kind of one way of finding that probability distribution. Let me show you another way. So now let's use our notation, okay? We said that capital N represents the population size. In our case, 6. Lowercase n will represent our sample size, In our case, in this example, 2. R, as we mentioned, represents the number of successes in our population. And in this case, it's also 2. And finally, the difference between N and R, capital N and R, is going to be the number of failures. And again, quotation marks, because this is relative to what you are interested in. Okay? In the population. In this case, 4. Right? Now let's think. Oh, yeah, right. So 6 choose 2 is going to give us the different possible combinations or possible samples that can result from this experiment. And that happens to be 15, right? We already found it using R. Now let's think about the number of distinct combinations with exactly 0 successes. So let me write it down here. Number of distinct combinations or samples with exactly 0 successes. Well, one way of doing that, and we had a homework problem where you had to do something like this. It had to do with a raffle and a group of organizers. Anyway, so to find this, all we have to do is, out of the population of successes, well, subpopulation of successes, 2, you have to choose 0. And then times, out of the subpopulation of failures, you're going to be choosing your sample of size 2, right? That gives you the number of distinct samples with exactly 0 successes, right? And let's find it using R. So it would be 6, instead of 6 and 2, we are going to have 2, choose 0, right? Let's see it here. Times 4, choose 2, right? Okay, 6. So finally, if we want the probability that y equals 0, because that's the one that keeps track of the number of successes in our sample, is just 6 divided by 15. Makes sense? 6 divided by 15. We can do the same for the other possible value, right? For 1, let's recycle what we did here. So now, instead of exactly 0 successes, we want 1 success. And that would be out of the subpopulation of successes, which has a size of 2, we want to choose 1. And then out of the population or subpopulation of failures, which is of size 4, we want to choose just 1. Let's find that number using R again. So let's change this one. This is going to be a 1, and this is going to be a 1. That's 8. Okay. Finally. Again, let's recycle this. Now we want Oh, and this would be a 1, right? Yeah. Now we want to do something similar for the other value. 2 successes. So now it would be 2 choose 2 times 4 choose 0. Then we do the math using R. So this guy turns into a 2, right? Now we want 2 successes, 0 failures. And that's just 1. Note how this matches with what we did before with the other approach, constructing the sample space and counting the outcomes. Okay. Now note that what we have here, for instance in this case, is just the following ratio. This 2 choose 0 times 4 choose 2 divided by 6 choose 2. Make sense? Okay, so now let me go back to our lecture notes. Here they are. I think that the slide that we're interested in is here. There we are. So this is the approach that we took, right? R represents the number of successes in your population, and F represents the number of failures in your population. Okay, so the probability of observing exactly Y successes is R choose Y times N minus R choose N minus Y, right? Divided by N, uppercase N, choose lowercase n. Okay? So the expression that you will find in your textbook is this. Okay? And we have some restrictions here, right? Note that Y is going to be less than or equal to R, which makes sense. I mean, you can't have more successes in your sample than successes exist in the population. Make sense? Just like in our case, we could have 0, 1, or 2 successes. We couldn't be able to observe 3 women in our sample. Our sample is size 2 on one hand, and on the other hand, the number of successes in our population was 2. Okay? Okay, so that's what these restrictions mean. Okay? Okay, so the second part of our problem was finding the expected value. Okay, let's find the expected value using the definition, and then I'm going to show you that there's a formula to quickly find it. Okay, so part B, expected value of Y. So by definition, we know that the expected value for a discrete random variable is just given by, the sum of Y times the probability of observing that particular value, Y, right? And you do the sum for all the Y's. Okay? So let me just remind you about that definition. Probability that random variable uppercase y equals a particular value lowercase y times y, that particular value, and we do that sum for all y's. Okay, so in our case we could have 0 women with probability 6/15. We could have 1 with probability 8/15, right? And finally, we could have 2 with probability 1/15. So clearly this is just 10 divided by 15, which equals 2 divided by 3. So roughly 0.6666. Okay. Now, as I said, it turns out that it can be shown that the expected value of a hypergeometric distribution is given by this formula: n times r divided by uppercase n. Right? Let's test drive this formula. So n times r divided by uppercase n. So using formula, expected value of y equals n times r divided by uppercase n. Our sample size was 2, remember. Our number of successes in the population of interest, 2, and the population size, 6. So that's 4 divided by 6. And yeah, that happens to be 2 divided by 3. So same thing, it works. Okay, now let me just say something. Note that there's a similarity with the formula for the binomial. Remember that the expected value of a binomial distribution of a binomial random variable is n times p. So note that we could rewrite this formula here as r divided by n times lowercase n, right? And you could think about this as the probability of success in your sample. So it's kind of like p. So n times p. It's similar, right? Okay. Now something that it's important, right? Something that is different from binomial distribution is that the probability of success for a hypergeometric distribution doesn't remain constant. Make sense? Think about it. For instance, we're drawing 2 people from this population of 6, right? If you think about the experiment sequentially, as you carry out, experiments for a binomial distribution, the probability of drawing a woman the first time around is 2 divided by 6, right? Because you have 2 successes in your sample. But once you choose one of them, right, for the second drawing, your probability of success is not the same. It's no longer 1 over 6. It becomes 1 over 5, right? Because you keep this one here. So you're not doing the sampling with replacement. You're doing sampling without replacement. Okay? So anyway, that's one of the main differences between the binomial distribution and the hypergeometric distribution. That in this case, the probability of success from one trial to the next doesn't remain constant. Okay? Okay. Now, how about we see how to do this using R? Okay? So let's use R. So first, let's take a look at the help for the following function, d-hyper, meaning the hypergeometric distribution. Okay? So, as you can see, that's our guy, the hypergeometric distribution, but I want you to see something here. So x is the random variable of interest, right? And C, it represents the number of white balls drawn without replacement from an urn which contains both black and white balls. Okay? Okay. So now M represents the number of white balls. So again, since X represents it's keeping track of the number of white balls, right? Then these guys are the number of successes in our population, M. And lowercase n, in this case, represents the number of failures, okay? And K represents the sample size, okay? So just keep that in mind, okay? So let's use it to make sure to verify that we're on the right track. So let's use the hyper to find the probability of seeing 0 women included in our sample of size 2. So M, remember, is the number of successes. So we have 2 successes. We have 4 failures, right? And we have a samples. We want a sample. We have samples of size 2. Make sense? Okay. So 0.4, and it is this guy, right? Let's go back to our probability distribution. 6 divided by 15, right? That's the same as 0.4, right? And we can find the next one, which is 8 divided by 15, right? Then last one, okay, which is 1 divided by 15. Okay? So anyway, just keep in mind that these parameters represent something slightly different. So M, we didn't use M in our textbook or for our presentation. Nope, we didn't use that. We used R instead. But I mean, just keep track of those parameters and it's straightforward. Okay, finally, let's try and find the expected value using R. So let me create an object, a vector that contains all the possible values for our random variable, in this case 0, 1, and 2. We can do that. We can make that assignment using the equals sign, and I'm just going to be retyping the name of the object I just created to make sure that I have there what I want to actually have there. Okay, now let me show you something. You could use this, okay, this function for individual values or for a group of values. So let me copy paste this. Oh well, actually I can do it here. So the x I am interested in is a vector of values, and now I have, you know, the probabilities for all possible values, right, meaning the probability distribution, and we know that all we have to do to find the expected value is this, right? Let me save it here in an object called prop_x, right? So that contains the values, right? The probability distribution, well, not the probability distribution, just the probabilities of our possible values. And then let's just do that multiplication, the vector x times the probabilities. Then we have this, right? That's a product, but we want the sum of those products, right, between y and the probability of that particular y, and that happens to be 0.666666, which is, you know, 2 divided by 3, okay, roughly. Okay, so let's summarize what we did today. Today well, in this video we talked about the hypergeometric distribution. We saw how we could derive the probability distribution from first principles, as we did before, and also with combinations. Now we have a formula as well for the probability mass function, meaning the formula that would give you the probability for a particular value of the random variable, and we also have formulas for the expected value and the variance as well. Okay, so later, if you want, you could try and, you know, for our example, compute the variance kind of a step by step, and then just use the formula to make sure that it works. Okay, so that's it for now. Please take care and keep working hard. See you next time. Bye.